Hello everyone and welcome to this familiarisation video for the cavitation tunnel, which is part of our marine propulsion lab at Newcastle University. I'm going to take you around various parts of the lab to show you how we conduct an open water test. So the purpose of an open water test is to measure the thrust and torque of a propeller such as this one, this model here, which is very typical of the type of propellers that we test in the cavitation tunnel here. The torque is obviously equivalent to the power that's being provided by the engine of the ship, and the thrust is obviously equivalent to the amount of thrust that the ship is being taken forward by, and therefore equates to the speed of the ship. And by taking the torque and the thrust, we can calculate the efficiency of the propeller, how good it is it operating in those particular conditions. The third parameter that we really think about is, third parameter is the water inflow, and that's equivalent to the ship speed. So there's a relationship between water inflow, RPM, thrust, and torque, and we can use those values to actually calculate efficiency. The cavitation tunnel's been testing propellers for nearly 70 years. So you can imagine that we've got quite a lot of propellers in the lab. And I just wanted to very quickly show these large propellers. These are part of the KCA series, which are classic sort of high-speed naval ship propellers tested in the 1950s. And they actually form part of a systematic series that are very famous in naval architecture. The propellers themselves are really heavy, and actually we can't test them on our modern dynamometer, so these are really just for antique value. I'm just down here on the ground floor of the tunnel, just to give you a view of the section itself. So we can see the cavitation tunnel over here, and it would normally be running clockwise, so the water's coming down through the far upright pipe and then down through the bottom. The impeller is driven by a motor that is in the blue box here, and the impeller actually is placed into the tunnel itself and runs through a shaft into the bottom section of the tunnel, and then the water is pumped up, and you can see how it's actually going into that larger section as it goes through the ceiling of the tunnel and up onto the top floor where we have the measurement section. So here we have the test section of the cavitation tunnel. What I can see behind me, behind these two glass windows, is actually a rectangular channel. It's about 1.2 meters wide by about 0.8 meters deep. And in there you can see there's the propeller, and that propeller is attached to the shaft and sort of torpedo arrangement, and I'll talk about that a little more in a moment. But let's explain where the water is going to flow. The water flows from my right over to the left, and therefore it's actually flowing around clockwise around the tunnel if we're moving forwards. This means that the propeller itself is facing into the flow and there's nothing in its way. So this is what we term an open water test, when the propeller is in otherwise undisturbed flow. This means you have to get your head around what this shaft is, because you may think it looks like the propeller shaft, but it's not. This is the dynamometer. We use the dynamometer to measure the thrust and the torque from the propeller. And it's also used to drive the propeller. That was driven by a motor that you can't quite see all of in the video, and that's positioned above the ceiling of the tunnel. Just as an interesting aside, you might be wondering about all the other equipment that you could see at the moment in front of the tunnel. Well, we've actually got our laser set up at the moment. So the computer system that's sat in front of the tunnel, and is just actually up here on the table, is actually controlling this sort of camera lens looking piece of equipment just there, and that is actually what we call a laser Doppler anemometry laser setup, and that's affixed to this gantry, so we can move that lens around and we can fire actually a set of laser beams into the flow, and by bouncing those laser beams off particles in the water, we can measure the fluid flow velocity very accurately and at a very precise point in the flow. So this is actually quite sort of technically advanced piece of equipment. We don't use it for an open water test, but I thought it was worth pointing out while we were here. Here's a view from on top of the tunnel. So I've just come up onto the top of the ceiling there, and you can see now looking down, this is a hat structure that sits above the dynamometer and is connected to this sort of bluey-green aquamarine motor that drives the propeller. So this is actually providing the torque, and then of course we measure the thrust from the dynamometer itself. It's quite nice up here because you get quite a nice view of the lab, looking very busy. And it's also worth noting, if we look up here on this side of the lab, of the tunnel itself, you can see there's another sort of hat box that's sitting on top of this large section. So as the flow comes up, it's in quite a large section prior to it being actually channeled down and actually contracting. We call this the contraction section, into the test section. And this box that we see here, that would be actually where we contain the free surface. So the tunnel is pressed full of water, and we'd normally put the free surface somewhere in that box, and that is where we actually apply a vacuum. So if you can see, the pipe that's actually running away from there is actually used to actually either control the air pressure that's acting on the water itself. So we can remove air and effectively lower the ambient pressure of the free surface. I'm just round the back of the tunnel at the moment, and I just wanted to show you this network of pipes very briefly, because if you start to look at the workings of the cavitation tunnel, it's a big piece of plumbing, and we have to move water both in and out of the tunnel as well as pumping it round, and we also have to control the free surface, so we actually have to think about the air as well, so we have air pumps as well. And that's what we can see here. Down here is actually our vacuum pump. We actually have two vacuum pumps, one and two, which we can actually use and are connected to the air pipes that are connected to the top of the tunnel, but also there's a network of water pipes as well. And these black devices, these are valves that are electronically controlled, so we can open and close valves to allow water to flow in or out of the tunnel. And so this is part of the filling and draining of the tunnel. We quite often have to bring the water out either to change specimens in the tunnel or even drop the water level completely in order to clean the tunnel or maintain it. We don't have to throw the water away. The water's pumped out to some outdoor tanks, so we can bring the water in and out from outside and keep the water maintained. So here I'm behind the control panel for the tunnel. Actually in front of here, what we can see is this big panel here is actually where we spend a lot of time controlling the fill level and the draining of the tunnel itself. But at the bottom we have a number of dials that also control the dynamometer, as well as the impeller that actually pumps the water around the tunnel. We also have a number of computers. We have a computer here that actually controls the basic functioning of the tunnel. So for example, controlling the pumps and the motors and the actual control systems. And then I'm going to rotate my camera. We also have another PC that is actually the output PC, and this is where your results come, for example, for your torque and your thrust measures. I'm actually running a simulated version of LabVIEW here, and we put this up online for you for lab work as well, so you can always open this up and have a look at how you can change the RPM of the propeller and therefore change the thrust and the torque. I'm going to do a very quick run through of what we would do as a procedure for an open water test. First of all, we'd make various measures of the conditions that we're doing the test in, including the air pressure, the water temperature. Obviously, we record the date and the time and the type of propeller we're using and any other observations. We would start by setting, in our case, we normally run with a constant water velocity. So we would set the impeller, which is our left-hand button here, and that would be used to control the flow speed past the propeller. We would then use our dynamometer control on the right here with another dial to actually vary the RPM of the propeller. I'm not going to run the impeller because it gets very noisy, but I'm going to switch the dynamometer on. So you can hear a click as the light goes on, and then we carefully turn this dial. I don't know if you can see or hear, but just behind me, you can see the propeller starting to spin faster and faster. We can actually see the RPM displayed on a little dial here, and also the RPM will also come straight into our computer system. Now that the propeller is actually spinning behind us, we'll be creating a thrust, and also we'll be driving it through a torque. So both of those values come out through our amplifiers. So thrust and torque from the dynamometer are basically a voltage, and that voltage is converted. In this case, at the moment we're reading a torque, so we've got about 1.6 newton meters of torque. You can see the thrust as well, about 32 newtons of thrust, and that's at about 200 revolutions per minute. So we can obviously spin that propeller faster. I'm not going to spin it too much more, just because we don't have any flow speed, so we don't want to overload the propeller too much. You can see that propeller's going nice and fast now. And we continue increasing the RPM at regular intervals. We calculate the values of RPM we needed to get ourselves a complete set of J values over the range of J that we need, and we'd be recording it on our computer system. And so this allows us to log the data by logging either 50 or 200 samples of force and torque measures, and it logs those samples, then will also give you an average. So it's able to actually plot out the thrust and torque values and calculate the efficiency.